Aha, okay. Cool. Welcome back. So let's see here. Your reading was already due. Your homework is due on Tuesday? Monday, so do that. Hopefully this homework isn't so bad. I think. Nods? Did anybody start it? Did we start? See, that's the thing. You guys complain when like, you know, we get our homeworks out late. But the reality is you don't start it until right before it's due anyway. Like, I don't feel that bad. But the next one will go out on time. And the next one is challenging because this one's a little bit easier. So get excited. I think. Right, so let's see. Other than that, I'm going to try and get your course proposal things graded by the end of the weekend. I'm sorry your professor has a chaotic month or two here. Any other procedural things that I'm forgetting? I think it's pretty normal. So next week, I am out of town all of next week. I will be close to email or Piazza or carrier pigeon or whatever your preferred means of professorial contact is. There's no class on Tuesday because it is an MIT holiday. It's sort of the extension of Patriots Day that makes the parody of odd-even course lectures work out in the Institute. And then on Thursday, this class is Tuesday, Thursday? It totally is. Yeah, on Thursday, Sebastian will be teaching optimal transport, which is a topic you should all be familiar with because it's my research field, and also because it'll be on your homework. Again, because it's my research field, it's an easy, area for me to write a homework problem about. Yeah, so that's the plan for next week. What that means is I won't have office hours. If you guys want, the week after, I can schedule extra ones or something, and we can have some conservation law. Okay, speaking of conservation laws, let's talk about exterior calculus. This is my least favorite topic of all of 6838. It's a popular topic to cover in a geometry processing course, so I feel morally obligated to do it for at least one lecture, and we're going to get through it together. Because this is, the reason as a researcher I got into geometry is it's a field I can draw pictures of and think about in a spatial fashion, and the whole point of exterior calculus and related disciplines is to get rid of all of that and turn it back into symbols, which is exactly what I was just really terrible at, as you guys have seen in previous lectures. So we're going to make this work. So, right, so if you guys recall from last time, we went to a lot of work to define a bunch of complicated objects that were much more complicated than the geometric things that we've already thought about, right? In particular, instead of vectors, we spent our time defining and manipulating objects called one-forms, right? Remember that a one-form is like an operator that takes dot products with vectors, right? In other words, it's a linear thing that takes as input one vector and outputs a scalar. Yeah, and so we kind of thought about differential one-forms as kind of like row vectors, whereas the vectors we talked about so far are kind of like column vectors, right? So when you put the two together, you multiply, you get a scalar. Yeah, and to go from a vector to a form and back are these musical isomorphisms, right? These sharp and flat operators. I can never remember which one is which, so if I get it wrong, I'm probably wrong. But you guys can catch me. I'm trying to preface this so that when I start making mistakes, you won't be surprised. And we talked about assorted things, how to take inner products, this analogy involving onions, which is totally confusing, but more importantly, the fact that differential forms are involved in how you take integrals, right? And that's what's going to come up a lot today, is how to understand things like divergence theorem, Stokes theorem, all these good things in a somewhat unified language. And then we're going to see that we can almost make it work on a discrete surface modulo a few things that we're going to have to sweep under the rug. Namely, so what we're going to define and what we started to define already are a few different operators, right? Things like going from one forms to two forms by taking a derivative, taking a wedge, and so on. And we're going to talk about a third operator, which is something called the Hodge star. By the way, Hodge star, if you take math courses, typically occurs much later. In the applied world, it seems to appear earlier for whatever reason, as it seems to be important. I don't know what you make of that, but in any event, you go to all this work to define this thing, and then in discrete exterior calculus, you can kind of sort of make it work. So we're going to make a D operator that truly behaves like D. We're going to make a star operator that kind of behaves like star, and we're not going to be able to define a wedge. So that's where we're going to end up today. Okay, right. So we already talked about integration and how that kind of suggested this notion of a two-form. Remember, where a two-form is kind of like a flux measurement device. So I give you two vectors which define a window, and then this is measuring the flux of some field through that window. Yeah. Okay. And the key properties that the thing had are that they're alternating and bilinear. Right? Remember what alternating meant, which is that if I took the inputs to my two-form and I swapped them, that I got minus the thing that I had before. And that makes sense in the flux thing, right? Because it's kind of like taking my window and flipping it upside down. So now the flux is negative. Yeah? Okay. Cool. So that's about our story so far. Yeah? And that leads us to this notion of a differential form, which is for every point P on a surface, or in general a manifold, it doesn't have to be a surface. A differential form is an operator attached to every point on the surface. Just like a vector field is a vector attached to every point on a surface, right? So now we're going to have like a K form attached to every point. And this thing takes as input K vectors and outputs a real number. And it's K linear, meaning it's linear in each of the slots independently, and alternating, meaning if I swap any of the two inputs, I get minus what I had before. So you guys see that what we've covered so far is a special case of this. Yeah? Have I lost anybody so far? Because it's going to be real boring if we're lost here. Okay, cool. And so like for instance, the differential one form on a surface is just another sort of way to encode a vector field, right? They're basically kind of dual to one another. What about a differential two form? Any guess? It's actually just a scalar. We're going to see that in a minute, specifically on a surface. So the key thing to remember when you deal with these K forms, which is somehow easy to get confused because we think a lot about intrinsic versus extrinsic geometry. There's now a third dimension you have to worry about, right? Like so a surface is a two-dimensional object sitting in R3, and then for a K form you also have that number K, which doesn't have to be 2 or 3. So like a one form would be like a vector field on a two-dimensional surface in three-dimensional space. So now we got 3 different dimensions we got to deal with. So if I want to take an integral, what's kind of the only dimensionality that makes sense? Well, remember in some sense, these things are like measuring areas of parallelograms. You know, it's like a two form, one form's kind of like a dot product or length. Yeah, so what we're going to find is that a K form makes sense as an object you can integrate on a K-dimensional object. Okay, cool. And so the way that I like to think about it, that I've kind of encouraged you guys so far, is that they're like flux sensors in some sense. In fact, I went on Google Images and I managed to find physical devices that roughly approximate K forms for different choices of K. I was pretty proud of this, I'm not gonna lie. Right, so a one form is kind of like, you see this guy standing in his what do you call these things? Waders, you know, the rubber boots. And the stream is moving past him, and he's got this stick, and what's on the end of the stick is like a little sheet of, probably not cardboard, probably like metal. Right, and so there's a force measurement device, and as he rotates it, the force changes, and that has to do with the sheet interacting with the velocity of the water. Right, like when it's parallel, the force is 0. When it's orthogonal, it's big. Yeah? And similarly here, I have like a little window, and I have my blowtorch. If I put my blowtorch parallel to the window, I have a very directed blowtorch, then the window will not experience any heat, and as I direct it toward it gets more. Notice in both of these things, to get my sensor to make sense, what did I have to do? The dimensionality had to add up to the dimensionality of the space. Right, so here the stream is sort of two-dimensional, and you had like a one-dimensional sensor and a one-dimensional vector field, which is your stream. And here you have like a two-dimensional sensor and a one-dimensional kind of stream of stuff going into it. And that's not a mistake, right? That's sort of the way that these objects work. Okay, so let's do a tiny bit of algebra. First of all, right, so let's see here. So there are sort of two related properties that we can get by just plugging in a basis, and that's that the space of K forms is one-dimensional, the space of K in Rk rather, and the space of K forms on Rn is nil when K is bigger than n. Yeah? So let's prove that second property first. Yeah? So this is actually pretty straightforward, I know, because Lorenzo and I did it 15 minutes before class to make sure that I wouldn't get it wrong, so now I'll get it wrong here. Right, so let's say that I have, let's prove this second fact. Right? So I take K is bigger than n, and I have a K form, right? So omega is a K form on Rn, right? So a different way to notate this, if I recall, is like that, by the way, if you like slick notation. That's a lambda. Okay, and what we want to show is that omega equals 0. You guys have any ideas how I could do that? So what are the properties we have? All I know is that if I take two inputs to this guy, and I swap their ordering, then the sign changes. And I know the thing is this thing is linear. Yeah, that sounds like a good idea. So let's say I want to evaluate, I'm going to try really hard to distinguish between omegas and W's. This is a problem in this lecture. So let's say that I have omega of V W. It's a very pointy W as they go. Yeah. Remember that I can write V and W as in a basis. Or oops, actually, this is a K form, right? So rather than V and W, let's do V1 through VK. Yeah. Yeah. Okay. So of course this thing is really. So I already managed to screw up my indices a little bit here, but that's okay. Right. So one way to view V1 is I can write it in the standard basis, and what am I going to get? I'm going to get that this is like V1 I EI, like that, right? So really. That makes sense? So all I'm doing is just writing all of these guys in the standard basis. This lower index here isn't really a lower index. It's just because there's K inputs to this thing. Yeah? Okay. So by linearity, I can take all of the scalars and pull them out of this expression. Yeah? And so what am I going to get? I'm going to get a sum, whatever, K times of omega of what? Well, here we're going to get kind of like V1 I1 to VK. I guess K, like that. So here the i's are the indices of all these different sums, but the 1 through K is always fixed as the order of the input into this thing. That make sense? Times EI1, EIK. This is why I hate this branch of math. There's like indices within indices. Yeah. Okay. Here's the thing. There's K terms here. Yeah? Oh, in fact, just for fun, I can pull all the scalars out, right? So this is, of course, equal to sum over all the stuff of omega of EI1, EIK, right? Where these are just like all the different possible choices of I1 through IK. Right, times V1 I1 multiplied together all the way to VK IK, like that. That makes sense? So all I've done is confuse myself and apply linearity. Yeah? Approximately in that order. Okay, so how many things are there here? There's K of them. And they're all indices in the range from 1 to n. Yeah? So remember that n is less than K. So there's something useful from discrete math you remember. It's called the pigeonhole principle, right? So I have n holes and K pigeons. There's more pigeons than there are holes. It's kind of a tragedy for the pigeons. So what can I say about at least one of the holes? There's at least one hole with 2 pigeons in it. Another way of putting that is that at least 2 of these EIs are the same in every single term in this sum. What do we know anytime there's 2 things? Well, I could have swapped their order and got minus that expression. But when I swapped the order, I actually didn't change the expression, right? Because it's the same E in both cases. So no matter what, this thing is 0. That make sense? I see a few furrowed eyebrows. Essentially what we convinced ourselves is we put in a basis, we put out all the linear parts, and we just left the basis terms back. And each time we have omega evaluated on K different terms, but necessarily that means there's the same input twice into this omega here. And that's enough to convince yourself that every term here is 0. Cool? So we just proved the second thing on the screen here. Yeah? This is good news. What this means is that like we've been talking about differential K forms, but really there's like a finite set of bases to worry about, right? Like so on a surface there's 0 forms, 1 forms, and 2 forms, but there's no 3 forms. Yeah? And similarly in a volume there's 3 forms, but there's no 4 forms. Whew. Okay. So similarly, the space of K forms is one-dimensional. Roughly, the proof is the same for the first 2 lines. Yeah, but then think about what you end up with left here, right? So in each case, so here if K is equal to n, right, then all of the terms are going to equal 0 except for the one with E1, E2, E3, E4, E5, all the way to En. Maybe permuted around, but that's okay because I can reorder them. And that's it. So there's just a scalar in front of omega of E1, E2, E3, E4, E5. Yeah. So that covers both of the things on the board. Notice that these are just algebraic properties. In fact, I think if you take some algebra classes, you learn about exterior algebra with no manifolds involved. It's just an interesting algebraic object. Any questions about that? These are just calculations. These are totally formal. Okay. So, right. So now we know a little bit, right? What do we know? We know that 1 forms encode vectors. We know that a couple other strange things. We know that 2 forms and 0 forms in the 2-dimensional space are both 1-dimensional. I know that sentence is hard to parse. Think about it for a second. So by property 1 here, yeah, if n is equal to 2, right? So if k and n are both equal to 2, then the space of 2 forms is just 1D. But so is the space of 0 forms. So somehow there's some duality between functions and 2 forms on a surface. Yeah. In 3D, is that the case? No. But somehow the 3 forms and the 0 forms are dual to one another. Yeah? So there's starting to be some structure that kind of arises here. And let's see a parallel structure. So when you guys took pre-calculus class, you defined this cross-product operator. And probably at the time, you dutifully wrote it down, and you did lots of calculations. You put I, J, and K in a matrix. You determined and all that good stuff. But here's the thing, this thing as a product, this thing that you're calling the cross product is super weird, right? It like doesn't behave like a product at all. And somehow we all happily believe that, but we don't think about it a whole lot. Yeah? So first of all, when I take the cross product between 2 vectors, I do get something where the units change, that's fine. But what happens if I take a vector and I cross product with itself? Like it's 0, right? And what sense does that make? Is that a property of like any product you've ever heard of? Well, no, right? Like typically when you take like dot product of yourself, you get the norm. Take a number squared, you get positive thing. So what the heck sense does this thing make? And to make matters worse, the dimensionality somehow is variable, right? Like I think every single smarty pants pre-calculus student out there says, okay, so we define vectors on Rn, and then suddenly you define this cross product operator for me, and it's only on R3. To make matters worse, sometimes you talk about cross products on R2, and then you have to kind of like pull in a normal vector somewhere. Like some weird stuff happens, right? And so a different way of describing that is, if I take the cross product of 2 vectors in the plane, this is in some sense a scalar, right? Because it's always parallel to the normal of the plane. If I take the cross product of 2 vectors in 3D, I get another vector. Nothing about this looks like a product. Yeah? And that's because it's not really a product. It's closer to what we're going to call a wedge operator. In fact, I think if you take math in Europe, this is kind of an American thing, right? Actually, I'd be curious. Our French student, did you learn cross product as a cross product or as a wedge? As a wedge. Yeah. So that's the way it's notated on the other side of the pond. Did you? Actually, I'm curious. Yeah. So it's not a country by country thing. Yeah. So if you like our diagram where you have this onion probe, which is a 1 form, yeah, then you could construct a 2-dimensional onion probe by superposing them on top of each other, right? So now I get little square onion cells. Yeah, so if I stick in 2 needles into my onion, my product of 2 onions, and count the number of cells that come in the common refinement of these objects, then I get some new operator which measures areas. Yeah, in fact, I could do this more than one time, right? I could get a wedge product. I think a more mature way to draw this picture was provided by Keenan here. So, right, so somehow, like if I take a cross product of 2 vectors, there's sort of 2 different ways to think about it, right? One is that it's like the normal to a parallelogram. The other is that it's actually just describing kind of the structure of the parallelogram, right? Like you know everything you need to know. You know its area, you know it's the plane that it sits in. And so somehow there's some duality there. And what we're going to see is that the wedge product of 1 forms is a 2 form. Remember that let's think about two forms. What's the dimension of two forms in R2? 1. What's the dimension of cross products in R2? 1. So they're just scalars. What's the dimension of two forms in R3? 3. Did we just guess that, or because we're extrapolating, or can you guys prove it? Let's actually prove it. It's not so hard. So let's say that I have a 2 form in R3. Yeah. So that means that I can write omega as equal to what? A1. Right. I evaluated on A1 E1 plus, I guess for consistency, A2 E2 plus 3 E3. Right. So this is all the vectors I can have in R3. And similarly, I have B1 E1 plus B2 E2 plus 3 E3, like that. Okay. So remember, this thing is bilinear, so I can expand it. Yeah. And so what am I going to get? I'm going to get. So first of all, if I have A1 E1 and B1 E1 as the two inputs to omega, what do I get? 0, right? Because there's an E1 in both of those slots. Yeah. So I have A1 B2 omega of E1 E2. I have A1 B3 E1 like that. B2 A2 B1 omega of E2 E1 plus, and then the A2 B2 term goes away for the same reason. Yeah. So now I get A2 B3 omega. Is this fun or what? E2 E3, and then finally I have all of these things. So I have A3 B1 omega of E3 E1 plus A3 B2 omega of E3 E2. Did I miss anything? I don't think I did. No. So is that it? So the space of two forms, right? Somehow it's parameterized by these numbers. So what's the dimensionality? 6? Wrong. Why? What did we forget? These are alternating, yeah? Good, you walked into my trap. Right, so in particular, omega of E2, E1 is the same as a minus omega of E1, E2 by definition, yeah? And a magic thing is going to happen, which is I'm going to get A1, B2, that's one of the E1, E2 terms, and then I'm going to get minus A2, B1, yeah? Okay, so now we're going to get A1, B3 for the 1, 3 term, and then we have a 3, 1 term over here. E1, E3. And there's a third term, which is A2, B3 minus A3, B2 omega of E2. Yeah, there we go.
Is it just like n choose k?
Is it n choose k? Absolutely. But what else can we, what does this expression look like? Looks like a cross product, yeah? That's not a mistake, yeah? So that's exactly what's going on inside of these k forms. However, it's easy to say it looks like a cross product, but if you're really persnickety about it, you might say, but wait a second, Justin. We started with 1 forms and we ended up with a 2 form, so the cross product is somehow slightly different. Do you see that? Let's try that again. So, right, a cross product takes in 2 vectors and gives you back a third vector. Yeah? What happens if I have a 2 form? Well, so somehow, you're right, there are 3 terms and they happen to look like the coefficients inside of a cross product. That's true, but notice that I've kind of mixed 1 and 2 forms here. Yeah? So something a little weird is happening. Because I have 1 forms which correspond to the e's, right? Those are like vectors. But then I ended up with 2 forms because it's like things with 2 inputs. Right? Like, for instance, what is E2, E3? What vector does that correspond to? Right? It's going to require a little bit of thinking. In fact, we already kind of know, right? Like, it's got to correspond to E1, but we haven't worked that out algebraically yet. We're going to need one more operator for that. That's going to be the Hodge star. OK. So in effect, you can think of the wedge as kind of like a generalization of cross product. So we can define, in fact, we can define the wedge form to be exactly the thing that gives you a cross product. This is the operation we're going to do. So this thing is a way to take two one forms and give you back a two form. Yeah? And the way that you define it is that alpha wedge beta evaluated a vector u v. It's a two form, so you need to have two guys in there. Is exactly this determinate expression here. And so somehow if you can double check that this object satisfies all the criteria it needs to satisfy to be a two form. Namely, if I swap those two inputs, I get minus what I started with. Not terribly surprising because it's a determinant. Yeah. OK, and in fact, in case that wasn't generic enough, here's a nice way to view it. So let's say that I take sharp of alpha and beta, so I get two vectors a and b. Yeah, so the vectors corresponding to these two one forms. Then I can evaluate the wedge at u comma v, just using that expression I had before. So this is the definition, yeah? And then I'm going to plug in the expressions for alpha and beta. So that's just what's going on here, right? So alpha of u is a dot u by definition, because a is just the vector sitting underneath the one form alpha. And if I just rearrange this expression a little bit, I can get this. This is just algebraic. You guys know what this thing's called? It's called the quadruple product. And so notice that there's two things hiding here, right? One is that there's an A cross B, yeah? So in fact, to take the wedge, what really comes out of the wedge, like the coefficients of this two form, are just knowledgeable about the cross product between A and B. That's it, yeah? And then in particular, this two form gets, when you crank through the definition, it's like A cross B dot product with the cross product of U and W. That's one way to view this thing is these two guys form a parallelogram, these two guys form a parallelogram, and this is like the area of, right, like remember what the normal, the dot product does? So this is like the normal, so this is like the angle between their normals. So it's sort of like the shadow of one parallelogram on the other. And that's exactly what's going on here. So the key point is that we define this weird product operator, this wedge thing, which takes in two one forms and gives us back a two form. But hiding inside of that two form is the cross product of these two vectors. You see that? It's kind of a sneaky trick. OK. Right. So in case I've lost you, let's make it a little more complicated. So now let's raise this to any dimension. So far I've told you how to take two one forms and make a two form out of them by taking basically a fancy version of a cross product. Now let's take a K form and an L form and make a K plus L form out of them. And here's one way to do it. So what we're going to do is define something called the symbol or the sign of a permutation. Have you guys seen this before? Sometimes this pops up in like algorithms class, like when you talk about sorting. So the idea is if I have a sorted list of numbers and I have another sorted list of numbers, right? Then I can do like bubble sort or whatever my favorite sorting algorithm is that just keeps swapping pairs of things. And I can count the number of times that I swapped. Yeah? And the sign of a permutation is -1 to the number of swaps. And one thing that you can check is that only depends on the ordering. It doesn't depend on the particular way that you decided to swap from one guy to the other. So by convention, let's say that the symbol of 1, 2, 3, 4 is 1. What is the symbol of 1, 3, 2, 4? -1, right? Because I only have to swap one time to get from one to the other. How about 1, 3, 4, 2? Any ideas? 1, right? Because one thing I can do is put the 3 here, right? So that makes 1, 3, 2, 4. Then I can swap again to get 1, 3, 4, 2. Did 2 swaps, -1 squared is 1. That's what's called the sign of a permutation. Yeah?
So it's sort of like just like an invariant for a sequence of numbers.
That's precisely right. It takes sequences of numbers and it divides them into two sets, the odd permutations, the even ones. Yep, great observation. Yeah. Notice it kind of, like if you think about permutation matrices, you can kind of convince yourself there's some nice linear algebra way to understand that as well. Yeah, great question. Okay. So you guys have any idea how we're going to define the wedge of two forms? Sorry, like two K forms. Or K and an L form. Well, remember that after I take the wedge, I need another form. And so in particular, I need a thing that alternates. That's going to be a problem. Like, let's say I have two zero forms. There's like two numbers. If I multiply that, and I want to make a one form out of it, I got to be a little bit careful, because if I multiply them together, it's not clear how to make a thing that, I guess you need two vectors in order to do this. If I have two vectors, I need to make a two form. If I just like take their dot product or something, it's not clear where the alternating structure comes from, right? And so if you look at the wedge product definition, it does it in kind of a sneaky fashion, where it says, I'm going to make the wedge between alpha and beta, right? So if alpha is a K form, beta is an L form, the wedge is a K plus L form, meaning that it takes in K plus L inputs, right? So what would be a really simple way to take a product? Well, it would be to take the first K guys and put them into alpha, take the next L guys, put them into beta, and then just multiply those two together. That's like some kind of product. Yeah, but we say, well, shoot, that thing that's not alternating. Yeah? Like if I had two one forms and I did that, like it's very clear that that's like it's not even symmetric, yeah? Okay, so what do we do instead? Well, we take every possible permutation of V1 through Vk plus L, and we take the first K of those and put it into alpha, and the remainder put it into beta. We multiply those two things together, but when we permuted, right, we kind of flipped the slots that they were in, but remember we have this convenient alternating property. So to take care of that, we put a -1 to the sign of the permutation in front of it. And this object is a thing that you can and should check is truly an alternating K plus L form. And the nice thing is that it generalizes cross product, dot product, and a lot of other stuff if you do it right. Okay? In particular, it satisfies a few properties that are easy to kind of eyeball. The anti-symmetry property says if I flip the order of my wedge, well, I don't get just minus what I started with. I get -1 to the K times L. That kind of makes sense because it's like the number of swaps you need to kind of move all of those guys from one slot to the other. Let's see here. It's associative. That's pretty clear from this expression here. And it's distributive. Actually, that's also clear from this expression. Yeah? Okay. By the way, A wedge A is equal to 0. Why does that make sense? Well, now in this sum, for every positive term, there's another one where I flipped it backward and I got a negative. Yeah? And so this property comes out. Now, whenever we talk about exterior algebra, we always cover the wedge product because it's actually really critical to get the sort of complete theory. One interesting thing we'll see when we try to discretize is that this one is the one that doesn't work out. In fact, it's kind of tricky to get a discrete wedge product. There actually is one that's derived in Hirani's original thesis on this kind of stuff, and it never gets used because it requires some interpolation, which is a little bit weird. Okay. So I have a basis for one forms, right? That was dx1 through dxk, or I guess dxn here, right? And that was just the dual of each of the standard basis vectors. So I want a basis for k forms. I can get it pretty easily. That's just the wedge of those guys with no repeated indices, because with a repeated index, what would I get? 0. Good, you guys are better at this than I am. Okay, and that concludes the sort of topological piece of exterior algebra. Right, so what do we have? We have k forms in n dimensions. We have a way to multiply them together. Okay, so let's make things more complicated. So first of all, let's say I want to take the dot product of two one forms. So now we're going to start adding geometry, right? So far, it's just been kind of algebra. And dot product is a way to measure length. What's like kind of the only reasonable way to take the dot product of two one forms? Like, there would be some really, like there wouldn't be order in the universe unless it were the case that I sharp those two one forms, so I convert them back to vectors, and I take the dot product of those, right? If those two dot products didn't agree, you'd have a very weird story to tell. So indeed, we make a definition, which is the dot product of two one forms is nothing more than the dot product of their sharps. That makes sense? This is just kind of a reasonable extension, because remember that this is just secretly a complicated way to talk about vector fields. Yeah? And so we're going to keep going back to that language. But more generically than that, we can take this definition and extend it in a really tricky way to the dot product of two k forms. This took me a long time to kind of convince myself why this was the right thing to do. So what you do is you take a basis for the two sides. You construct a matrix out of that basis where you evaluate your k form on every pair of possible inputs. Then you take the determinant of that big guy. And what comes out is what we're going to define to be the inner product. One thing you should do is double check that, like, if you put the same thing in twice, you get something positive right? Because otherwise you'd be in trouble. But in particular, kind of the way that you can think about this is just like constructing a parallelogram out of all the vectors that you have and then taking the area. That's kind of roughly what's going on here. Yeah, and so for instance, here's the inner product of V wedge W with A wedge B. Right? So what did I have to do? Well, I took vectors, I flatted them so that they're forms, then I wedged them, and then I inner producted them. Right? So by definition, right, that's what's going on. This is a determinant. I just read off that formula from up here. Yeah? And in fact, if you work it out, that's exactly this quadruple product that we already saw. Yeah? Notice that this really is an inner product, right? Because there's a dot product sitting there. It's symmetric in the two inputs, yeah? And bilinear. So now we have a way to take inner products. For the most part, if this is uncomfortable stuff, that's okay, because it's actually, we're going to be on surfaces, and there are only two inner products you have to worry about, one of which is dot products between vectors, and the other of which is multiplying scalars together. Yeah? So it's only in volumes where things get a little funky. Okay. But one way or the other, this allows us to add one more piece to our algebra. If you're wondering, if you take differential geometry class, this is usually amortized over like 6 lectures, and it's less terrifying. Okay. And that one vector is going to take us. So what do we know how to do so far? We know how to take a K form and an L form, put them together, and make a K plus L form. We're going to add one more operator that takes a K form just by itself and makes an N minus K form. And this is what's going to allow us finally to get our cross product. Right? Because remember, when I wedged two one forms together, I got something that kind of looked like a cross product, but I got a two form out, so I didn't quite get it. So there's something we need to do to take two forms back to one forms in R3. And secretly, we know the dimension of those two things is the same, right? So it kind of works out. And that operator is called the Hodge star. Okay, so now let's talk about the Hodge star. The Hodge star is defined by this relationship up here, and let's do a sanity check and make sure it makes sense. So here's the point. How many dimensions is the set of n forms in Rn? 1, right? There's only one n form in Rn. And it's just dx1, wedge dx2, wedge dot dot dot, wedge dxn. That's it. That's all you can have. We already showed that. Yeah? So that operator we're going to call dA. To make matters worse, we're going to define a D operator in a minute, and it's not going to have to do with this dA. This is just notation. So dA stands for the area form, which is the wedge of everything possible. Okay? So the area form is sort of a unique n form, and so what that means, the only thing I can do is put a scalar in front of it. Yeah? And so the Hodge star operator is kind of funny. What it does is it says, okay, let's say I have a K form. Then I can get an n minus K form by saying there's another guy where if I wedge them together, well, if I wedge a K form and an n minus K form, what do I get? I get an n form. So that's just a scalar that's sitting next to dA. So the Hodge star is the thing so that when I wedge them together, I get an inner product. Okay? And this is complicated and annoying to think about. One way to think about it is an orthogonal complement, and in fact, let's make that precise. Okay, so let's say that I have a one form alpha, right? So alpha is equal to, and just in R2, because that's enough already. A1 dx1 plus A2, like that, right? That's our basis for one forms. So secretly, alpha is just encoding the vector A1, A2. Yeah? And similarly, I have another vector beta, right? So he's B1 dx1. Okay, so first of all, what is alpha beta dA? How do we read that off? This is just a dot product. Huh? So this is like A1 B1 plus A2 B2 dx1 wedge dx2. Okay? Just kind of by definition. So that's one side of this expression. What's the other side? Well, let's call star of beta. Let's just call him C. Right? So we're going to have C1 dx1 plus C2 dx2, like that. Okay? So what is alpha wedge star beta. Well, let's just write it out. So this is a1 dx1 plus a2 dx2 wedge. This expression here, c1 dx. Yeah. Now what's going to end up happening? So basically we only know how to do one proof on exterior calculus. We're going to keep using it, right? Which is that anytime you have something wedged with itself, you get 0, right? Because it's alternating. Yeah. So what you're left with is the cross term, right? So you're going to get a1 c2. And then now you have a2 c1, but notice that the x2 is first. So you've got to put a minus in front of it. Okay, right? Now remember, by definition, these two things are equal. And so now, notice, what can you see here? Well, C1, C2, let's write it this way. And here we have B1 and B2. Yeah, so C1 is the thing next to A2 with a minus sign in front of it. So there's like a -1 there. Yeah, and C2 is the thing next to A1. I did it wrong already. C2 is next to A1, so it looks like, I guess the right way to read it is like that. So you have A1, B1, you have A1, C2. So these two have to equal each other. There we are. So C2 equals B1. So it's like that. And similarly from the other guy, you get like that. Okay, there we go. What is this matrix? Rotation by 90 degrees. That's it. So the Hodge star in the two-dimensional plane is extremely simple. It just rotates 90 degrees. And in some sense that makes sense, right? Because you're thinking about Hodge star as a thing that gives you an orthogonal complement. Like, remember that a two-form kind of is like a thing that's like encoding a pair of vectors, right? Then the Hodge star of that is going to be like the normal vector to that plane, weighted by the area of the parallelogram. Here, the Hodge star, the only orthogonal complement you have is just to rotate counterclockwise. By the way, the counterclockwise part is by convention. There's nothing special there. Yep. Okay. So now I think we're finally done with all the nasty stuff. So now, right, so we have, again, notice that we keep doing the same kind of pattern. We first do something algebraic, and then we talk about the whole thing on a surface at once. Yeah, we just did some new algebraic stuff, right? We introduced a Hodge star and a wedge, and now we have to think about the space of differential K forms on a manifold, which is kind of like one K form per tangent plane, right? So for instance, a vector field is a differential 1 form. Yeah, okay, right, and that's notated as follows, right? So if this thing is a set of alternating K multilinear forms, then typically omega K is the assignment of one of these guys per tangent plane, just so you guys can kind of parse through a geometry textbook. Okay. Then you can actually define an inner product of these things, and it's not terribly surprising how you would do that, right? Because what is this thing? At the end of the day, if I have two K forms on a surface, then when I wedge these two things together, this is a scalar times dA. And this is this intuition for taking dA, that that's the number that's integrable. So now you're just integrating a scalar over your manifold, and that's an okay thing to do. Yeah? So this is how you would inner product K forms on like a surface as opposed to just at a point. This is just complicated language for saying inner product them at a point and then integrate that over the surface. Yeah? Notice, let's say that these two guys were vector fields secretly. They're 1 forms. Then all this notation is saying is what? Just saying take their dot product and integrate over the surface. That's it. That's all that's going on. Okay? So, now that we've put it on the surface, we can start to do some really crazy stuff, right? Because so far, these are all sitting on different tangent planes. But now that we have a surface, we can differentiate them, right? We can walk along the surface and ask, how does my vector field change as I move from one point to another, right? So, and we've already actually kind of done that for 0 forms. Right? Because how do we define this? Remember this differential operator that keeps popping up? What is this thing? This is a 1 form. Do you see that? So if I have a scalar function on a surface and I take d of that, the way we've defined it in like lecture 4 when we talked about curvature, Remember, what is d of a function? We define it to be this thing where you kind of take a directional derivative in a vector direction. So the thing that input a vector and output the dot product of the gradient with that vector. And now we know that this is just a special case of a one form on a surface. Yeah. So now, if you want to go, you go to a bar, you want to show off your fancy language, you can see that really what we did is we computed the exterior derivative of a zero form on our surface. Yeah. So the one missing piece that we have in our puzzle is an object called the exterior derivative, and that's how you differentiate these things. Okay, so let's talk about exterior derivatives for a minute. So we're going to keep resorting back to like the one form and zero form case because those are the ones that are easy to think about, and then essentially just extrapolate using like product rules and all that good stuff. Yeah. So first of all, I think actually now you guys are all equipped to read this fancy notation here, right? So remember that we defined the gradient to be the vector that secretly df is taking dot products with. We actually did this before we talked about differential forms in this class. So now we know. Remember what the sharp operator does. It converts one forms to vectors. Yeah? So secretly, the gradient operator this whole time was nothing more than df sharp. And similarly, if you want to go the other way around, if I take the flat of the gradient vector field, I get back df. So there's a nice duality between this and just calculus. In case you hate this stuff, A, so do I, and B, you're going to do a lot of it on your homework. So get excited. Okay. Right. So that's how we differentiate zero forms, but that's like not terribly exciting. If we just wanted to differentiate functions on a surface, we could obviously do it with much simpler language. So now we want to differentiate K forms because we're suckers for excruciating pain around here. Yeah? So how are we going to do that? Well, the problem is when I differentiate a K form, if I do it the wrong way, I'll end up with something that isn't alternating anymore. Do you see that? So like, let's say that I had a two form on a surface. Right? Now I could like take two vector fields on my surface, evaluate that two form at every point on the surface. That gives me a scalar function. Yeah? And then take the gradient of that thing. Right? That gives me a vector field. And then take its sharp, or flat rather, and that convert it back to a zero form. But it's not totally clear that gives rise to an alternating thing without knowing those two vector fields that went in at the beginning of that story. In particular, like, if I swap those two vector fields, do I get the same thing? Yeah, not so clear. Yeah? So in the exterior derivative, we kind of do like the wedge product. We like wanted to take a directional derivative, but we can't because we're going to leave the space of alternating stuff. So then we just start taking directional derivative of everything in every possible direction, putting -1 in front of it. And this actually has a reasonable way to interpret. So one thing you might ask for fun, and this is actually the topological way to motivate a lot of this stuff, is let's say that I have a one form. Yeah, so remember a one form is secretly a vector field. And let's say I want to ask a question, which is when is my one form actually d of a zero form? There are like too many numbers and letters flying around today. So remember, so what is that? Let's think in physics language for a second. What is that telling you? That's asking when is a vector field conservative? Yeah? Like when is a vector field really the gradient of a function? But the language we're going to use today is when is a one form d of a zero form? Does anybody know the answer to that? You guys remember from calculus class? If I just give you the vector field? What was that? No curl, yeah. Yeah, I guess on the plane that works out. Path independent, that's another condition. The third one you can check is that the derivative of the x component in the y direction is equal to the derivative of the y component in the x direction. This is exactly like no curl in the plane, yeah? Okay, so let's think about what that means. So let's say that I have one form. Remember that a one form I can write on a basis, so secretly is the sum of a bunch of fi's, which are just scalars, which is good. We like scalars, we know how to deal with this, times dxi. Yeah? So, okay, so what do I know? I know the second derivatives commute of functions, right? If I take a derivative of a function in I and then j direction, it's the same as taking j in I direction. So I can subtract from both sides and get 0, right? So in other words, if this guy is d of a zero form, then I have this expression here, that the derivative of the jth component in the I direction is equal to the derivative of the ith component in the j direction. That make sense? So there's a really slick way to check this in the language of forms, which is I subtract the right-hand side. Right? So it's just dfj dxi minus dfi dxj equals 0. And I multiply that. Right, so in fact, let's just write it down. So, right, so I have dfj dxi minus dfi dxj is equal to 0. Yeah, that's certainly true. I just subtracted from both sides. One thing I can do is multiply this just for fun by the wedge dxi wedge dxj. Yeah. Why would I do that? Well, you see a minus here. Somehow minuses are important in this theory. Yeah. So I could write this in yet another way, right? Which is dfj xi dxi wedge dxj plus dxj wedge dxi equals 0. Right, because I swapped the order of the two. And why would I want to do that? Well, notice one thing, that this is true for all I and j, this expression. So a different way of saying that, which is kind of funny, is to just say this. Do you see that? Because actually this is a basis for one form, so secretly this is just checking this expression over all I and j pairs. So a nicer way to write that sum is exactly what's on the screen here. Do you see that? Because that's just using this relationship that I wrote. I changed that minus into a plus. Yeah, sneaky, huh? So here's the kind of funny thing. This wedge is hiding a lot, right? I'm basically leveraging that alternating property to say that even though there's secretly a minus sign that I'm checking, I just kind of rolled it into this sum and relied on the fact that these guys are not ordered anymore. Does that make sense? So this object is a thing that I'm going to define to be D of a one form. Yeah? What does that mean? So let's say that I have a function, so a 0 form, and I apply D to it twice. What do I get? Kind of by definition. Okay, so a function satisfies this property here. So when I put that expression in here, what do I get? 0. Right? In some sense, that's how I motivated this object, right? I said that if I apply D to a one form and I get 0, that tells me that that secretly came from the gradient of a function, right? That's how we defined it. So in other words, we sort of just by we kind of vacuously just said that, at least for 0 forms. Yeah. This is going to become a really critical property topologically. Okay. Anybody know what this property is called? For D? Yeah, that's okay. Right. So anyway, this is now a way to define D of a one form. It's the thing that you check is equal to 0 to check if your one form was really the gradient of something. This is kind of nice because somehow one way to think about this is when you think about the set of vector fields, you can decompose those into two things, right? They're like the things that are gradients of functions and the things that aren't. Yeah? And so somehow the way that you're going to differentiate between those two is the D operator. And that's going to be a structure that we're going to lift to higher dimensions. Okay? So to lift that to higher dimensions, we're just going to do this axiomatically, and I'm going to stop drawing pictures because like enough already. We're thinking of D like a derivative. And now we're going to give it a product rule, which is almost the product rule you would guess, right? So D of alpha wedge beta, you put the D inside, but you need a -1 to the K term to kind of move the D past all the alpha terms, is roughly what's going on here. And this is just an algebraic way to take D from 0 forms and 1 forms now to K forms, right? Because I can always write a K form as a wedge of lower guys. Okay, so now let's get concrete. I keep saying that. And let's talk about integrals. Okay? So I claim that it makes perfect sense to take the integral of a K form over a K-dimensional manifold. And why is that? So let's think for a second about what's going on. So the area form is the only K form on a K-dimensional manifold, right? dx1, wedge dx2, wedge dx3, wedge dx4, and so on. what do you think I'm going to put inside of that thing? Like the standard basis, right? So that's kind of like the area of like a little rectangle or a little cube or whatever sitting on my object. And so that's like really the dA that's going into my integral. Yeah? So in a line integral, for example, like a really nice thing happens, right? Which is that I evaluate my one form, right? Because the line is one-dimensional, on the tangent to my line. This gives me back a scalar, and now I can multiply by ds and integrate the whole thing together. This is like an area element, so secretly he's taking into input, this like a little bit of the curve that's going in. Yeah? Okay. Right, and similarly for surfaces, that makes a lot of sense. And what we're left with is one crowning achievement of exterior calculus that we are not going to derive in this class. But I encourage you to read the Wikipedia page. And that's something called Stokes' theorem, which you've probably heard of. And in fact, I think on your homework, you'll derive some special cases of this that'll relate it back to the Stokes' theorem that you've probably seen in calculus. So I'm going to defer to your homework for you guys to do that, which is going to require putting together all the things that your instructor has managed to confuse them about so far. And that, all these things, Stokes' theorem, Green's theorem, divergence theorem, curl theorem, what are some other ones? I think there's like some fancy electromagnetic phrases that people use to refer to these, right? All these different things where you integrate on the boundary of a domain or you integrate in the interior and they're equal to each other. All of them are summarized in this really slick expression, which is that the integral over a domain of D of a form is equal to the integral over its boundary of that form. Now let's first of all make sure that this parses. In general, the D operator takes me from K forms to K plus 1 forms. Yeah? So if I have a K-dimensional manifold, then the thing I've got to integrate is a K form, which means omega is a K minus 1 form. Does the right-hand side parse? Yes, right? Because the boundary is one less dimension than the volume, and so is omega relative to d omega. Yeah. So at least the expression kind of parses. Yeah. And this is just a fancy way to state all of these different vector calculus identities in one shot. Yeah. This leads to a nice property, which we kind of hinted at before, which is that d squared equals 0. In fact, I guess if you believe that Stokes' theorem is true, you can derive this in kind of a funny way, where you do it kind of differentially, like in a little patch. But why does that make sense? So let's say that I integrated d squared of omega over some patch, and now I apply Stokes' theorem twice, right? So the first time I get the boundary, the second time I get the boundary of the boundary. What's the boundary of the boundary? Yeah, it's not a damn thing. So you're integrating over nothing and you get 0. Yeah? So this d squared operator is just 0. Okay. And that's going to be a nice thing. If you want to translate from vector calculus to this language and back, one thing that you can check algebraically, which secretly we already proved, but I got myself all confused and upset, is that all of these things are true. And in fact, now you guys are equipped to kind of go back and check all these identities. And you can see why I hate this branch of math. Right? Because they take things that are totally natural and you can draw pictures of and convert them to sharps and flats and d's and stars and all these different operators. But the nice thing is that now, like if you want to sort of, you want a proof of Stokes' theorem or like, Green's theorem, what are you going to do? Like the integral of divergence, well, you can write divergence like star d star, and then you're going to apply, just the generic Stokes' theorem that we have, and then you're going to go from right back to left, and what you'll end up with is one of these assorted expressions, all combined into one. Yeah? In fact, a reasonable proof of Stokes' theorem, if the only thing you care about is surfaces, I guess, is to check all of the assorted theorems that you learn in calculus class and then just stick them all into this notation. But that wouldn't be too exciting. Okay. So thankfully that concludes our exterior calculus. And as with many things in this course, what we're going to see is that the discrete version of this is actually much more intuitive. Thank God. And this is actually really a theme that I love about this class. Like I have always struggled to understand certain pieces of Riemannian geometry, and as you can probably see, I continue to. However, the discrete case is often more concrete, right? Like so similarly, think about Gaussian curvature, right? Like we defined Gaussian curvature on a surface. It took a little bit of work, right? We had to do the derivative of the normal vector. We had to define the normal vector. We had to define second fundamental form. It takes trace, all that good stuff. Not as trace, it's determinant rather. And then what did we do for like a triangle mesh? Well, we just like summed up angles adjacent to a vertex and said like, okay, well that minus 2 pi. Like somehow something similar is going to happen here. Like all this crazy stuff will get much, much more concrete, which is good because I like concrete. Easy to code too. And so discrete exterior calculus has been a buzzword in geometry world for, what, about 10, 15 years. Essentially, it's just like a discrete version of everything that we've already covered here. There's a way to make it work on meshes and other structures. Okay? So, in order to do this version of exterior calculus, what we're going to need is an oriented simplicial complex. Or if you don't like that, you can think about a triangle mesh. Right? So, but this is a triangle mesh that isn't like a Mobius strip. So every triangle is accompanied with, I guess, a counterclockwise direction, or a normal vector. Yeah? And remember we built up these crazy data structures like the half edge? This is where these are going to come into play. We take all the nasty stuff from this class and glue it into one 20-minute lecture here. Okay? So, what we're going to do is we're going to orient every element in our mesh. So not just the triangles. So every triangle is going to have an ordered set of edges. Every edge is going to have an ordered set of vertices. And the order is going to be arbitrary on everything except for the triangles, where the triangles are going to be in like a counterclockwise way. Okay? Well, I guess that's kind of arbitrary. The only thing that matters is the relationship between them. We'll see in a second. Okay. And we're going to need one other object, which is the dual complex of our mesh. And this is the thing that takes k simplices and replaces them with n minus k simplices. Does that sound familiar? Huh? Huh? So like you have, for instance, you have triangles. You can replace every triangle with a vertex, right? Every edge with another edge. Yeah? And a tetrahedral mesh. Think like here's two tets, in case you're wondering. So what is, let's see, what's a neighboring pair of tets? Well, there are two ways to think about it. One is that they share a triangle. That's the primal structure. But now there's an edge between them. A triangle is how many dimensions? Intrinsically? Come on, I don't ask hard questions. 2. An edge is how many dimensions?
1.
No, 2.
1. An edge is a straight line. Yeah, it's 1. So the dual of a triangle and a tetrahedral mesh, which is like a 3 manifold, goes from a 2 simplex to a 1 simplex. So it's starting to sound an awful lot like the Hodge star, yeah? Okay. And that's the trick in exterior calculus, is that we're going to keep k-forms on k-dimensional elements. But we're going to need one additional piece of information, is that occasionally our elements will be on the primal mesh and occasionally they'll be on the dual mesh. We're going to have to work with both of those at the same time, just to make our life a little harder. Okay? Right. And the trick in discrete exterior calculus, just like a lot of things, is not to store k-forms themselves, but to store their integrals. Yeah? Does this sound familiar? Like, remember when we talked about curvature? We never actually stored curvature, we stored integrated curvature. Exactly the same thing happens here, which is that we're going to keep track of the integral of a k-form. So for instance, a discrete zero form is kind of a discrete primal zero form. We'll come back to that in a second. It's like one number per vertex. What's the integral over like a k-dimensional thing? A zero-dimensional thing? It's just a number, kind of vacuously. Yeah? So in this case, it doesn't matter. A discrete one form, I'm going to think of as the integral of the one form along an edge in my triangle mesh. Notice that this alleviates a lot of the problems that you might have heard in Ed's lecture. It brings many more. But in particular, sort of the only one-dimensional objects that I have on the triangle mesh are arbitrated, are kind of oriented in weird ways. They're not lined up to my vector field. So what can I do? I can't keep track of my vector field if I want to store it on edges, but I can keep track of the dot product of my vector field and that edge. Yeah? And so indeed, that's exactly what I'm gonna maintain. Is I'm gonna think of a vector field as a one form per edge, which is the integral over that edge, or roughly the dot product between your field and that edge times the length of that edge. Roughly. Yeah? And then finally, similarly, I can think of a discrete two form as like an integral over a triangle. Okay? Now here's the really cool thing that's going to happen. Remember the Stokes theorem business? Okay. So let's say that I have the integral of d of a form over an edge. What is that equal to? Well, it's equal to integral over the boundary of the edge of the form. Yeah? What is this form? This is a zero form, yeah, because it's over an edge. Okay. So if I want integral of d omega, and omega is a zero form on an edge, I don't actually need to know anything more than the value of omega at the two endpoints of that edge. Right? This is Stokes' theorem. Right? So the integral over the edge of d omega is nothing more than the difference at the two endpoints. Yeah? So if I have a zero form, like omega, an integrated zero form technically, but whatever, integral on a point, it's a boring thing. Then secretly, I can get integral of its exterior derivative, and I have made no approximation. Do you see that? This is sneaky, very sneaky. Okay, similarly, right, so this is the big trick, is now I can think of my D operator, which before is some crazy thing that involves wedges and all this weird stuff. It's just an edges by vertices matrix, which just subtracts things along edges. That's it. Notice I had to orient my edge. I had to decide which of these was vertex 1 and vertex 2. This is like too critical, so you just have to orient it carefully. That makes sense? Can we do a similar thing for two forms? Absolutely. Yeah? So in particular, let's say that I have an integral over a triangle of D of a 1 form. Right? So the 1 form, I know its integral along every edge. Yeah? So what do? I take this integral over the triangle, I apply Stokes' theorem. Well, what is this guy? This is just the sort of the sum of the integrals over the 3 edges. I have to be a little bit careful about the orientation of the edge relative to the orientation of the triangle. Yeah, because the triangle has a clockwise direction, so if the edge faced the other way, then I gotta put a minus in front of it. That's it. Yeah, so what is D? D is just a matrix again, and the only values in this matrix are minus 1, 0, and 1. That's it. So now, one thing that you can check, in fact, if you didn't like all this crazy math we did, you can check this relationship, and it holds exactly. Do you see that? Unfortunately, this notation is totally misleading, because really these are 2 different matrices, right? So the first D is like from 0 forms to 1 forms, right? So this is an edges by vertices matrix. The next D is from 1 forms to 2 forms. This is kind of typical notation. When you multiply these 2 matrices to 0, together you get 0. And actually that's just by Stokes' theorem, right? Because we didn't make any approximations here. Does that make sense? So now we're going to get things like the Hodge decomposition of a vector field. It's just going to come from the rank nullity theorem in linear algebra. We're not going to need all this crazy topological stuff. Yeah? Sure. Let's see here. So I have a 1 form, yeah, that's omega, which I'm thinking of as 1 number per oriented edge, right? Which means if I flip the edge backward, I get minus that number. Okay, so if I want the exterior derivative integrated along a triangle, then I apply Stokes' theorem. That's the same as the integral around the boundary. And then what do? I go around the triangle in a counterclockwise direction. Notice that edge 2 disagrees in orientation with the orientation of the triangle. So that's why you get a minus in front of omega 2 here. Yeah. Other questions? This is a good question. It's easy, as you can see, this is easy stuff to get yourself all balled up. Okay. And the beautiful thing about this discrete exterior derivative operator is that there's no approximation necessary. If I happen to know the integral of a K form along every element of my mesh, I can get the integral of D of that form along every element of the mesh for free. And there's an equal sign there. There's no approximation. Of course, when do I ever have the integral of a form along the elements of my mesh? Never. But if I did, then I could do that. And the key observation is that D squared equals 0. I forget if you proved it in your homework this year or not. In previous offerings of this class we did. Yeah, but we removed it. Okay, well, maybe we'll prove it next time. Actually, you already have it, just kind of as a corollary of Stokes' theorem, actually. Okay, so that gives you a D operator, and now if we're going to go through our algebra, we need another guy, which is the star. Notice I skipped over wedge, because it's actually not clear how to define that on a mesh. Okay, and the trick to the Hodge star is that roughly what it's going to do is translate you from the primal mesh to the dual mesh, and that's actually extremely concrete how you would do that on the triangle mesh. So let's say that I wanted to go from a primal 2 form, so that would be like a number per triangle, to a dual 0 form. Any guess how I would do that? Remember that I never keep track of quantities, they're always integrated. So roughly, I started with a number integrated over a triangle, and I want to get kind of a pointwise value. How do you think I do that? Just, not quite. I can't evaluate it the dual vertex. All I know is the function integrated over the triangle. I don't know its value. But like in the absence of any other information, I might as well divide by the area of the triangle, and then I roughly get something pointwise. That's it. That's the Hodge star. That goes from primal 2 forms to dual 0 forms. We're going to skip over the one form Hodge-star for just a second and think about the primal zero form Hodge-star. So that goes to dual two forms, which is kind of like the integral over this pentagon here. So how do you think I'm going to do that? Just multiply by the area of this thing, yeah? So the Hodge-star is extremely concrete. The only thing I'm left with is one kind of weird Hodge-star, which is the one that goes from primal one forms to dual one forms. By the way, take a look at this diagram. It's already kind of suggestive. Yeah, because what do you notice about the blue edge and the green edge? They're pretty much orthogonal to one another. Yeah? What do we know about the Hodge-star one forms? It rotates by 90 degrees, right? Everything is working out. There's order in the universe here. Yeah? So in particular, our Hodge-star matrices, right? They kind of like integrate over cells. They rotate 90 degrees. They divide by points. This is where some approximations appear. Do you guys see that? Because what did I do? Like if I wanted to go from the primal 2 form to the primal 0 form, I divided by the area of the triangle. That kind of gave me the average value on the triangle. It didn't really give me the value at the center point. Yeah. So that's where approximation happened. We're going to see it's actually compatible with approximations we made when we talked about finite element method. It's kind of amazing. Okay. Right, so now let's do our Hodge-stars in some more detail. So first of all, this guy we already covered. This is 1 over area. Yeah. Now, the primal 1 form to the dual 1 form. What does it do? It does 2 things. It rotates by 90 degrees. But the other thing it has to do is account for the fact that the primal edge and the dual edge don't have to be the same length. Right? And it's the second thing that you have to be a little bit careful about. And this is by convention. There are a lot of different ways you could define this Hodge-star operator. So for instance, you could put this at the barycenter of the triangle and then just compute the length of this edge, the length of that edge, and put their ratio there. It's perfectly fine. But there's one particularly elegant choice here, which is to remember that these two guys really somehow, spiritually, they want to be orthogonal. Yeah? And for lack of a better idea, maybe we put the orthogonal edge right at the midpoint. Yep. So I have a picture that looks something like this. I have 2 triangles. There's one. See, when I get myself confused, I start drawing things bigger. So it makes it better. And now I'm going to just bisect that edge because I kind of know where to put the dual edge. I might as well put it in the middle. Yeah? And I'm going to make it orthogonal because we know that Hodge-star rotates by 90 degrees. Notice if I did this barycentrically, like I just averaged these 3 vertices, that actually wouldn't happen. This wouldn't end up orthogonal. So what happens if I take the orthogonal bisectors of edges? They all intersect at a point. Yeah? This is what, the circumcenter, some damn thing from high school calculus class that I can never remember. So, let's think about this for a minute. So, what happens if I scale my triangle by 2? What happens to the ratio of these 2 edge lengths? Let's just scale the whole mesh. Nothing. Yeah? It just depends on these angles. Like that. Huh? So if you guys were to guess, just given the last few lectures that we did on the Laplace operator, what do you think the ratio of this edge length to that one is going to end up being? It's going to be the sum of the cotangents of these 2 angles. Yeah? So I will let you guys check that at home. It's just a high school trigonometry exercise, right? You have 3 perpendicular bisectors, and you want to know the ratio of these 2 lengths. You have everything you need to work this out. Yeah? So, yeah, more precisely, it's 1/2. So anyway, this is a good exercise to do at home if you don't remember your high school geometry kind of stuff. It's a good trigonometry exercise to get this thing. And it's basically an application of constructions you've already done in class before. By the way, you could ask a totally reasonable question, which is why did I put this edge at the midpoint of the primal edge? And in fact, people asked that in research a couple years ago. And our colleague Fernando worked out this idea of a weighted triangulation, where for every edge, what you keep track of is the distance along this edge where your orthogonal dual guy ends up. If you think about it, that's sort of controlling the size of the dual cell associated to every vertex. This is some way to like keep a different area measure on your surface. And this will relate to what you'll hear about from Sebastian on optimal transport. Okay. And now you have everything you need. So the one missing Hodge-star operator you need is the thing that goes back to two forms, and that's just multiplying by area again. So you see, the Hodge-star is this crazy thing that, kind of commutes with Wedge and gives you an inner product. But on a mesh, it's just the thing that, like, takes you to the dual element, and the only way you kind of know how. Yeah, it's pretty nice. There are many different ways to get Hodge-star. We already talked about this when we talked about finite element. Remember we talked about lumped mass matrix? This is somehow exactly the same thing, right? You're converting from scalars to integrals. Yeah? And so this is a totally reasonable way to do it. If you want to be compatible with this picture here, then you really should take the area of this cell where you take the orthogonal bisectors. I mean, if you look at this diagram, you can see that these are like really clearly not the orthogonal bisector here. So that gives you a different kind of cell around a vertex called the Voronoi cell. People don't always love this because it can actually give you negative numbers sometimes. Because you can get diagrams that look like this, where you can see that actually the surface center ended up outside of the triangle. And somehow that is like a weird thing to think about on a triangulated surface. And actually there's a little bit of engineering that goes into this. So different people choose different Hodge stars. I don't think there's a whole lot of science in terms of engineering which one people choose. It's similar to the mass matrices. The typical choices are the barycentric, the Voronoi one, which has this nice advantage of being kind of consistent with the picture we've drawn so far. There's also something they call the mixed cell, where you do Voronoi until you don't like it anymore, like until that vertex leaves the triangle, and then you revert back to the other one. If you guys identify interesting literature on how to choose these, I'd be curious to see it, because I don't know of any. The mixed Voronoi cell is kind of funny. Basically, it just double checks that you never leave the midpoint of the opposite edge. If you like this kind of stuff, the similar set of authors actually talk about, like, for instance, can you optimize the Hodge star for different applications and so on. This is like the beginning of a very giant iceberg worth of funny math and cool stuff you can do on a mesh. But for now, the one thing that I want to kind of leave you thinking with is that we now have this totally crazy diagram. Do you guys see this? We have the primal mesh and the dual mesh, right? So this is, in each case you have, so here's on a tet mesh, right? So you have, for tetrahedra, you have primal zero forms, which are vertices, primal one forms, which are on edges, primal dual forms, which are on faces, and primal three forms, which are on tets. And the Hodge star operator keeps you on the same element, but interprets it differently. Right? So you have these like two copies of the tet world where the star brings you down and up, right? And the D takes you left and right. You can define an additional operator delta. So if I want to go left, how could I do it? I could do star, D, and then a star. And that thing is called delta. And I have a way that I can move around all in this mesh, in this kind of diagram here. And what happens if I move left twice? 0. Remember, d squared equals 0. So there are a lot of cool properties of this thing. Anybody know the name of this in mathematics? This is called the de Rham cohomology. You have k forms, and you have these d operators that link them all together, and you have this special property that d squared equals 0. And so in practice, what do? Well, you build up about 1 billion different sparse matrices, right? All the different d operators you can think of. So like in this diagram, there's 1, 2, 3, 4, 5, 6 of them. By the way, secretly, this D and that D are transposes of one another. You can double check that. So there's really only 3 of them. But you do need 4 Hodge stars and their inverses. And now you can multiply them together to build up even more complicated stuff. Yeah? So for instance, one thing you can do is take inner product of forms. And if you want that to be a dot product, remember that you have this something wedge something else. Well, it kind of works out, right? If you have a primal form and a dual form, if you put the star on it, you flip it back to the original guy, and then you can take their dot products. It's kind of like multiplying by the area element, taking the dot product and summing. Yeah? And in particular, one thing you can double check is that this kind of funny integration by parts property holds. And this is sort of a duality between D and the delta thing that we derived before. And this just, you can derive by just kind of following paths around in that diagram, right? There's nothing more going on here. So, at the end of the day, what can you do with all of this machinery? You can define a Laplace operator. Yeah? In fact, one thing that you can check in theory, remember if we go all the way back to our smooth stuff from a long time ago, Okay, so div is star d star, grad is d, yeah? So you want Laplacian, it's star d, yeah? We have a d, we have a star. What do you think happens if we multiply all these things together? We get the cotangent Laplacian matrix, exactly where we started, yeah? So you can skip all of today's lecture and just do it with finite elements and you'll get exactly the same thing. So somehow there's order in the universe, right? We did this purely geometric construction. We did nice things involving edges and their duals, and all it does is give us yet another motivation for the same Laplace operator that we had before, which is kind of fun. By the way, notice that there's star d, so there's two different area factors. Why is that? What is the left star doing? That's actually the mass matrix in finite elements, right? Because remember that. So let's parse the Laplace operator for a second, then we'll call it a day. So, So, let's say I have a function f. Yeah? So f is a primal zero form. Now if I apply d to it, yeah, then what comes out of d? What's sitting here? So the d operators keep you in primal or dual. They don't flip, but they raise the index. So this is a primal one form. Now I put a star here. I get a dual one form. Now I do a d again. I get a dual two form. And finally, I put one more star here. I get back to a primal zero form. There's order in the universe. It all kind of worked out, right? I started with a function, I ended with one. But let's think for a second, what is this star? This thing is like 1 over the area of every Voronoi cell around every vertex, right? Because it's the thing that goes from a dual two form, that's one number per vertex, integrated over a Voronoi cell, and goes to a primal zero form, which is one number per vertex not integrated. This is 1 over area associated with the vertex. Right, so if I wanted to solve Poisson equation, how would I do it? Well, I would put like g over here. G is also a primal zero form, right? But I could put the inverse of this matrix over here. What would I have? I'd have on the left-hand side the cotangent Laplace operator. On the right-hand side, I'd have the mass matrix. It's exactly the same system of equations. Yeah, so everything works out. Life is good. By the way, in discrete exterior calculus, it's very hard to understand what the non-lumped mass matrix would do in finite elements. That's really strange if you think about it. Yeah, so maybe we'll leave it there for the day. Essentially, there are many different ways to understand this. One is that really this is just an encoding of a finite element theory that allows you to have K-forms. In fact, there's a finite element version of exterior calculus which is completely compatible with all this in case you really do care about fields. And I encourage you to look into the Whitney forms for the right basis for that, just like the hat basis on a triangle. And when we come back next time, we're going to talk about how to apply this machinery to computing the Helmholtz-Hodge decomposition. So taking a field and writing it as the sum of a divergence-free field, which is this guy. Notice it only circulates, there's no div. A curl-free field, meaning that there's no circulation, and a harmonic part, which goes around the donut. This is like the big takeaway from de Rham theory on surfaces. On triangle meshes, it's going to be really easy. It's just going to be linear algebra, basically looking at the null spaces of the different matrices involved here. Cool? All right, so next time, thankfully, you'll be listening to Sebastian rather than your instructor who hates this material so much. And then after this, we're back into comfortable ground for me. Yeah, so I'll see you guys in